We're continuing with Chapter 13 and continuing to talk about experimental design. So we're first going to talk about how to tell when the differences that we see between two groups is actually a large enough difference to prove our cause and effect or disprove our cause and effect relationship. So, does the difference make a difference? Different groups are going to have different means or averages, even if the treatment has no effect. Randomization causes the means to be different from group to group, at least slightly, so we expect there to be some differences. The question is, how big does the difference have to be to show that the treatment has an effect? If the differences are larger than we would assume to get just from randomization, then we can attribute the differences to the treatment. So in other words, is it more than what we thought it would be? Is there a larger difference than what we were expecting there to actually be? If so, then we know that it's from the treatment. If not, then perhaps the treatment didn't work. These differences are called statistically significant. So something is considered to be statistically significant if the difference between two averages is more than what we expected there to be. Then the results are statistically significant. How do you know when the difference is going to be big enough? Well, first, before you even go into the experiment, you're going to have some kind of baseline idea of what you would expect to get if the treatment doesn't work. So what is already in place. If it's significantly different from that, then we would consider the treatment to work. If it's within the range of that, then probably not. So let's take a coin, for example. If you flip a coin 100 times, you would expect to get heads 50% of the time. If we were to end up with 54%, that would be okay. That's within the range of 50%. If we were to get heads 94% of the time, then there's probably some kind of an outside influence, and that would be considered to be statistically significant because it's so much greater than the 50%. So, talking about experiments and samples, both experiments and samples use randomization. They just use it in different ways. Samples are taken from a population, and these samples are going to be random with the goal of representing the whole population. Experiments, on the other hand, may not take their experimental units at random. Again, we've kind of talked about this. If you're testing a cancer treatment, you're really only going to be using people who have cancer. However, we pick who ends up getting what treatment randomly. So it's kind of as though we do take them randomly from a population. It's just our population is extremely narrowed down. Another difference between experiments and samples is that experiments can draw stronger conclusions than sample surveys. So by looking at the differences across the different treatment groups, experiments cancel out bias. Because if each group could be biased, and as long as they're biased in the same way, it won't affect our results because we'll be able to see past that bias. So experiments are a lot less likely to have that bias, and they're also the only thing that we can really use to try and prove cause and effect. Control treatment. Suppose we heard that drinking a specific sports drink before running can cause you to run faster. We want to test this by drinking it and then go running. But we need to compare the time with the drink to the time of running without the drink. This treatment of not drinking the sports drink is called the control. So, how fast you normally run on your own. This control is different from controlling the situations. Controlling the situations in this case would mean that you would be running both with and without the drink at the same time of day, after the same stretches, on the same path. All of that would be like controlling the situation. Not drinking the sports drink is the control treatment. The control group is the group that receives the control treatment, and this is often the group that receives no treatment at all. This kind of leads to blinding. Humans are susceptible to errors in judgment. We are. We are naturally biased, and we are not random, and knowing things affect our thought process, whether we think they do or not. So when we know what treatment was assigned, it's difficult not to let that knowledge influence our assessment of the response, even if we try to be careful. If they are testing a migraine medicine and you know you get the drug, part of you is going to feel better because you know you're getting the drug. if you're testing the migraine medicine and you're in the control and you know that you're not getting medication, you are going to continue thinking that you have a headache longer than you may actually have it. In order to avoid that kind of a bias, we use blinding. So there are two main classes of individuals who can affect the outcome of an experiment. Those who can influence the results, so the subjects, the treatment administrators, or technicians, and those who evaluate the results, judges, treating physicians, etc. A single blind experiment is when one of those two groups are blinded. So one of those two don't know who was receiving what treatment. A double-blind experiment is when both classes are blinded. So both the subjects and those evaluating don't know who received what treatment. A double-blind experiment are the best experiments. There are some that can only be single-blind, and if that's all you can do, then that's all you can do. But ideally, you want your experiment to be double-blind. This leads to placebos. Often when we are being treated, the act of the treatment can have an effect. You think you're taking the medication, you immediately think you're feeling better. A fake treatment that looks like the treatments that are being tested is called a placebo. Placebos are the best way to blind subjects from knowing whether they are receiving the treatment or not. The placebo effect is when the subjects being treated with the placebo improve. This shows the importance of effective blinding and comparing treatments with a control. Using a placebo is important despite the fact that we get the placebo effect, because we kind of expect that. It also helps us determine what really is mental and what is not. To wrap it up, the best experiments are randomized, meaning from your very limited population, you randomly determine who receives what treatment. They are double-blind, so the subjects and the administrators do not know who is receiving what treatment. They are comparative, so they have a control group to be able to compare the treatment to a baseline. And they are placebo-controlled, so that way the people who are in the control group are unaware of what group they are in. That is it for tonight. I hope you guys have a great night, and I will see you tomorrow.